This video is just a quick note on spherical and cylindrical coordinates and the relationship. Cylindrical and spherical coordinates with a relationship to parametric surfaces. Okay. So the past day or so in lab we've worked on this particular parametric description, R of u comma v. We've looked at, say, for example, cosine of u, sine of u, comma v, where maybe u, if ever you write down a function, you need to write down the domain that the variables u and v go from in this case. So let's let u go from 0 to pi, and v go from, say, -1 to 1. Okay, and you'll notice here that u, since it's 0 to pi, the pi usually indicates that maybe we've got some sort of angular variable. U is our angular variable, and v is some sort of just number in this case. So to figure out the meaning of that number, you could get a plot of this function. You could just say parametric plot. It is a function in 3D, and it has two variables, so it's simple to type. We've worked on these in lab class, and you should probably recognize this equation before I type it as a cylinder. And let's let you go from 0 to escape. Type the word pi, hit escape again, and it'll typeset it to a pi. And then v goes from, say, -1 to 1. Now you should know the plot of this before we do it is part of a cylinder, and we can see here if we add axes labels that the z-axis is pointing straight up. So in this case, our number is a height. It's some sort of length variable, and it's the height of this cylinder. And this u is our angular variable. Okay, so here's the parametric surface, and the question is, how does this relate to spherical coordinates? Okay, for example, if u goes from 0 to 2 pi, then we'd have a full cylinder. Okay, now the thing to note here is this is sometimes hard to wrap the mind around. But we're so used to thinking about, sorry, my axes are a little bit crooked, but here's x, y, z space, right? We're so used to thinking about x, y, z space that you pick your favorite point P, and maybe we already know, like, O for origin, 0, 0, 0, and let's say you pick a point P to be 1, 2, 3. We're so used to thinking in rectangular coordinates that this point P, we don't think that this point P is just as the numbers 1, 2, 3. We think of it as 1 in the x direction, 2 in the y direction, 1, 2, 3 up. So we're so used to thinking in terms of rectangular coordinates that we think that the only way to get to this point P is by moving along this grid here, right? But so if you looked at this point P, the point P in rectangular coordinates is x is equal to 1, y is equal to 2, and z is equal to 3. Okay, but we don't have to think about this point P only in terms of rectangular coordinates. You can choose to think that every point, maybe as shown in this picture, that every point in this space is actually maybe on some sort of cylinder. So if you imagine that, you know, this space, instead of being filled with a rectangular grid is actually filled with cylinders of varying radii, right? So, and as this cylinder keeps getting bigger and bigger, notice that at some point, this point P is on the cylinder of some radius, and it's at some, right? This point P is on a cylinder of some radius, right? It's at some angle, okay? And it's at some height, z, right? So we are seeing here, okay, those three descriptions will get me to the point P, and every point P in space, every point P is on some cylinder, right? Okay, and that is the essence of cylindrical coordinates. Instead of using x, y, and z variables, you can use the variables r, theta, and z. Now, it was very convenient that we're so used to that z being up that it's so natural maybe to just draw our cylinders, right, with a height of z, okay? And this is where this problem comes in, this parametric plot. This is only the plot of a cylinder of with u as the angle variable and v the height, right? So if you have a point P and you want to write it in rectangular coordinates, you would just set the x variable to be some number, y variable to be some number, and z to be some number. Okay, but we can see here from the parametric description that in cylindrical coordinates r, theta, and z, the x has a different description. If you want to describe this point P in terms of the radius variable, the angle variable, and the height variable, to describe this point P, you need to use the functions r cosine theta, y to be r sine theta. This is acknowledging that this point P could be at any radius along here. And then the z variable is just z. Okay? And this problem is acknowledging our preference to have cylinders that are standing upright. Okay? We know that we could have changed the orientation of this cylinder and have put v here and then sine of u in this other, in the z entry, and then we would have had a cylinder on its side, right? And that would have been acknowledging that, maybe every point P in space is on some cylinder. But if you wanted to view them on cylinders of radii this way, every point P will be on some cylinder, some sort of cylinder that's facing along whose axis is running down the x-axis. So in that point, if you had chosen your cylinders this way, then you would have said that the cylindrical coordinates would be x is equal to r cosine theta, acknowledging that there would have been a radius. You would have had some sort of angle, right? And then z would have been r sine theta. And then instead of talking about a height, we would have been talking about a depth here to get to a point P. So then you would have just said y would be equal to y. Right? So you can do this for cylinders of every orientation, but this version is the standard. You have to make a choice about your orientation of your cylinders, and this is the standard orientation. Okay? So what we are talking about here in this problem is our cylindrical coordinates the standard that we're talking about is r theta, and the cylinder we're going to have being oriented upright. So the problems that we're going to be getting to, where we're going to be talking about triple integrals, right, over regions here. So maybe we have this part of a cylinder. So here's my x-axis, the y-axis, and the z-axis. And let's say that this part of the cylinder is going from between z is equal to 0 up here to a plane, say z is equal to 1. Okay. Now, if you want this region to be solid, right, as because we're going to be trying to do a triple integral over this solid region, then that means that we are on cylinders. Every point in here is on a cylinder of some radius, right? And every point in here is at some angle theta, right? And it's at some height z, and it is on a cylinder of some radius. Okay? So if we're having to integrate over this solid region in the xyz plane, the trick is to change the integrals to be integrals over your cylindrical coordinates, r, theta, and z. Right? And so the radius here would go from 0 to, say, let's say the radii of these things. This is a cylinder, and let's say maybe the x value goes to 4 and 4 here. So the radii would go from 0 to 4. Theta would only go from, theta is measured from the x-axis to the y-axis. So theta would only go to pi over 2 here. And z goes from 0 to 1. So if we ever get to a point where we're doing a triple integral, we're going to be changing coordinates, and we are going to be using instead this solid cube in r, theta, and z space. So that's how I'm viewing the cylindrical coordinates. There's actually a transform. There's a vector valued function in 3 variables that we are using implicitly here. Transform of r, theta, and z. There would be t1 as a function of r, theta, and z. You can write down a transformation here. t2 of r, theta, and z. And t3, r, theta, and z. And that transformation that we're talking about is r cosine theta, r sine theta, and z. Here is our transform. And what this means is that if you pick a point in cylindrical coordinates, if you have a point in cylindrical coordinates, say 4 r theta z, so here's a point in cylindrical coordinates, and you want to figure out, so that's the point 4 pi over 2, 1. So this point right there, what does it look like in this point? Where is that in the XYZ plane? What point on this solid is it? Well, that would be the point in XYZ space. You would have to transform the point 4 pi over 2, 1. And that means just plug this point into this transformation. So you'll get 4 cosine pi over 2, 4 sine pi over 2, 1. Which means that you're at the point 4, 0, 1. So this point right here transforms to the point 4, 0 in theta, 1 for z. So that would be this point in XYZ space on this cylindrical solid. If you wanted a point in the middle here, you should probably use the Cartesian coordinate, the cylindrical coordinates. Say change the radius to be 2. Maybe let the angle be somewhere in the middle between 0 and pi over 2. Maybe how about pi over 4? And let's say z is a half, right? So if you transform that to x, y, z, right, you'll get 2 cosine pi over 4. I'll leave that for you to do. Is probably 1 over square root of 2. 2 sine pi over 4. And then 1/2. You can convert these to decimals if you would like, but you'll find that you'll be somewhere here in the middle on a cylinder of radius 2. You'll be somewhere here in the middle at pi over 4, and then you'll be at an elevation of 1/2. So you'll be somewhere here in the middle of this solid. Okay, so that's cylindrical coordinates and how I'm viewing them as being related to these cylinders and these parametric plots. I'm viewing the space filled up with cylinders of different radii, and therefore your things that are changing to move in this space are the radius of your cylinder, the angle where you are along the outside of this cylinder, and where you are along the edge of the cylinder. And because we have to choose a convention, we choose the convention that our cylinders that we are using are facing upright, and we look at them of various radii. 2 times, for example, 2 times. And now your cylinder just got quite a bit wider. Okay? So that's cylindrical coordinates. I will, in the next video, talk about spherical coordinates.